Good afternoon, everybody. We're going to go ahead and get started with today's webinar. My name is Sean. I am our wireless product manager here at the US Zyxel office. As we go through today, if you have questions, and you probably will, send them in using the question and answer interface. Today is our Wi-Fi 101 webinar. So on this webinar, we're going to be covering a lot, not really our products, but we're going to be talking more about general Wi-Fi, how it works, common misconceptions, things that go wrong or people misunderstand that cause issues. We've already got a question come in here. Go ahead and answer Jeff. Jeff sent in a question already. So again, if you have questions, use the question and answer interface. So Jeff was asking about cloud management. So that's not something we're going to be talking about in today's webinar, but I will go ahead and answer that. I'm guessing he's talking about Nebula. So the Nebula cloud management platform is something that does work with our access points. The basic version of it is free. There is no limitation on the number of devices you can manage, the number of customers you can manage. And then there are some licensed options that you can add on that unlock additional features, primarily aimed at the MSP space. We do a monthly Nebula webinar where we go into much more detail on cloud management. But today we're just talking about Wi-Fi. So again, it's just going to be common misconceptions, explanations of how things work. I go through it fast because there are a lot of slides. It can be a little bit technical at times. Again, if you have questions, you can send them in. But in general here, I'm just trying to give you sort of a high level overview of what's going on when it comes to wireless. So we're going to start here with just one slide on Zyxel. So this is just who we are. So Zyxel has been around making networking equipment since back in 1989. That's when we got our start. Our US office has been in roughly the same location that entire 30 years. We've moved once or twice to bigger and better buildings in the general area, but we've been operating out of the greater Anaheim, Placentia area this entire time. We have over 1,500 employees worldwide. We've sold over 100 million devices, and our products are available in 150 different global markets. I'm here with the US office, or I guess technically the North American office. We cover the US, we cover Canada, and we are linked directly to our Central American office, which covers Central America and Mexico these days. So now we'll go ahead and get started. So we'll start talking here about some of the players. So if you've been around the Wi-Fi world, you've probably seen these names. There's the IEEE. They're the ones who create the 802.11 standards. It's an international group that is of engineers that get together and they create these standards. So that's where we get 802.11b, 802.11ax, 802.11n, etc. We have the Wi-Fi Alliance. Now, the Wi-Fi Alliance is primarily a group put together of the different manufacturers and resellers of wireless equipment. So back in the early days of Wi-Fi, one of the problems we ran into is, when we're reading a standard created by the IEEE, there was no one there to enforce that, your implementation matches the criteria in that official specification. And even in cases where you're trying to comply with it, there's always things and questions about how to interpret the written language and understanding how to do it. So a number of the manufacturers got together and said, hey, this is causing problems. Different vendors' products aren't talking to each other. So the Wi-Fi Alliance was formed to create some interoperability testing and certifying that those products can talk to each other. And since then, they've also focused more on these more recent terms as more of a marketing group. Marketing Wi-Fi. They're the ones who created the Wi-Fi logo. They're the ones who created the Wi-Fi name, I believe, or at least standardized on it. And they're the ones who recently rebranded, 11B, 11AC, 11AX as Wi-Fi 3, Wi-Fi 4, Wi-Fi 6, etc. You generally will see Wi-Fi certification on consumer-oriented products. You do not generally see it used as often on business class products. And then there's the FCC. So in the US here, FCC is the one who establishes what frequencies you can use, how much power you can use, how much bleed over you can have into band edge and things like that. So the FCC sets the rules. They don't do a lot of enforcing. The testing and certification is done by the manufacturers themselves. So the FCC sets the rules, then we have to submit our products to an independent third party to get those products certified. There have been issues in the past with certain people, say, violating those rules as to how much power output you can have. And in one case, Netgear, for instance, had to sue another vendor out there to force them to comply with the FCC rules. Basically, they had got the product certified, but the products actually being imported into the US under that certification didn't actually comply. So those are the three guys that we have that sort of deal with each other. We've got a question here from an anonymous attendee looking for solid information criteria for choosing between different Wi-Fi 6 access points. So we're not really going to have anything specific to those individual products today, but we are going to give you some good rules of thumb to use in different applications in general that apply across the board when it comes to selecting Wi-Fi equipment, but that'll be towards the end of today's presentation. Okay, on to the next slide. So just some basics here on radio waves. So basically, as the frequency goes up, the easier it is to cram more data onto it. But also as that frequency goes up, the range goes down. So I'm going to use an example here. Some of you younger guys out there probably won't be able to have experienced this yourself. But for instance, cordless phones, when cordless phones were relatively new in the US, they used the 900 megahertz frequency. So sound quality wasn't the greatest, but you could get ridiculous range. It was perfectly normal to be on a cordless phone call, be able to walk outside. In my case, I could walk across the street to a friend's house and still be able to maintain a phone call. Starting in the 90s, there was a push to move phones from 900 megahertz to 2.4. 2.4 spectrum was recently opened up, and it provided a lot more available bandwidth to share. So if you were in an apartment or a condo, you didn't have interference or have to worry about overhearing your neighbors, or at least that was the sales pitch. Sound quality went up with 2.4, right? 2.4 gigahertz, much higher frequency than 900 megahertz. So sound quality went up, but the range got reduced. So you can no longer, walk, or at least I can no longer walk across the street. I could go outside and around my house and still be able to have a conversation, but I couldn't walk over to my friends anymore. Then a little bit later in the 90s, they opened up the 5 gigahertz bandwidth. Same thing, 5 gigahertz higher frequency. But at this point, you could no longer use that phone outside. The signal didn't go that far. People with larger houses may not be able to cover their entire house in 5 gigahertz. So you saw the rise of repeater type add-ons to your base station. So you would have one base station and then add a second base station. You could have multiple cordless phones because the range wasn't as good. And it's the same thing with Wi-Fi. If you've been doing this for a while, you've probably noticed that you don't get as good a range when you're connected to a 5 gigahertz radio as you do with the 2.4. So again, radio frequencies are regulated by the FCC. And in general, if you want to broadcast radio waves, you have to have a license. Getting that license tends to be hard. Depending on the frequencies being used, it may be limited to certain applications. But they have opened up chunks of spectrum that you can use without a license. So that's that 900 megahertz band, 2.4, which we're all familiar with. That's 802.11b or G, or single radio 11N. And then the 5 gigahertz space. So basically anything that's using any form of wireless technology at home is probably operating in one of these three bands. So you have to share that band not only between your Wi-Fi devices, but between other wireless devices that you may have operating in your home or nearby. So in general, power is measured as dBm. So when you're looking at data sheets for business class products, you will normally see output power measured as a standard of dBm. If you are looking at consumer products, you will often see the power being stated as a matter of milliwatts. So dBm converts over to milliwatts. So Anonymous Attend just said that my audio cut out while I was answering his question. So the short version is I'm not going to have anything specific on those models, but I am going to talk about here towards the end of today's presentation, some general rules of thumb. In general, there's not that much difference from one AP to another, and you just follow these general rules. So we'll get to those later on at the end of today's presentation. Okay, anyway, back to radio waves here. So in general, as dBm goes up by 3, you are doubling the power output. So a 20 dBm product is putting out 100 milliwatts. A 23 dBm product is putting out 200 milliwatts, double the power. So if you went up to a 26 dBm, you would have 400 milliwatts of output power. So the reason people on the consumer side like to use milliwatts is because small changes in your dBm output power look like big changes if you're referring to it in milliwatt. On the business side of things, people generally prefer dBm because that's what the standards and the rules are based around. It's also really easy when you're using dBm if you're doing something with external antennas, which used to be really common, 5 to 10 years ago. Nowadays, most APs aren't using external antennas, but it used to be common to switch out the antennas. So you could take the dBi gain of your antenna and add it to the dBm output power of the radio and find out really simply what the total output power was. Losses for cables and things like that is also measured in dBm or dBi. So you can simply add and subtract to get your total output power that's coming out of that antenna. In general, in the US, the maximum output power you're going to see, and you're going to see this on 2.4 radios, is 36 combined dBm between the antenna and the radio, giving you, in theory, up to 4 watts of output power. So some other terms that you're going to run across a lot is signal to noise ratio, and this is probably the most important thing that tends to get overlooked the most often. So that's simply telling you the ratio of the strength of the signal you want to listen to versus the level of RF noise that surrounds it. So a good way to think about this is if you're having a conversation with somebody, their voice is the signal, and then any other noises around you are going to be the noise. So if you're sitting in an empty conference room, just you with one other person, the signal is going to have a really good signal to noise ratio because there isn't going to be a lot of background noise. But if you're, say, in a crowded bar on a Friday night, even if the person is talking at the same volume level, it's going to be hard to hear them because of all the other background noise, the sound of other people talking and other conversations you don't want to listen to, sounds of music, sounds of, the bar and drinks being made, that type of stuff. So even though the signal is the same, because the noise floor is up, it becomes harder to understand. And it's the same thing with radio waves. And then just in general, attenuation is a common term you'll see here. And that's just saying how much that signal degrades or weakens as it travels from the place where it is broadcast. Signal degrades pretty quickly as a factor of distance. And as it goes through objects and things like that, it will degrade much more than if it's going through simply empty, dry air. So if you really want to calculate how far that signal is going to go, this is the formula that you want to use right here. So basically you take your dB output power, and it's 20 log 10 of D, the distance, 20 log 10 of the frequency you're using, plus 92.45. There are calculators out there that you can use where you can punch in all the specs on the access points you're using, and it will tell you the theoretical maximum you can go. So that's telling you how far the signal in theory can go. And it doesn't require a lot of power in theory for the signal to go really far. A typical home, say 400 milliwatt home router in theory can send that signal a mile. But realistically, we know that that doesn't happen. You're lucky to get 100 or 200 feet. And that's just because there's background noise that you're having to deal with. There's other things going on which can degrade that signal, things like that. But if you're doing outdoor point-to-point links, there are a number of calculators on the internet you can use to try to figure out what you need to be able to go as far as you want to. And then just we've got a list here, a table of, other things that are going to affect your signal. So you can see here a signal going through a glass window will drop by about 3 dB, or it'll essentially have the power of that signal that's going through it. In the case of a window that's been tinted with a metallic tint, it can degrade that signal by up to 8 dBi. Medium wall up to 10 dBi, floor and ceiling 20 to 25, depending on what they're made out of. So another thing to keep in mind here when we're talking about Wi-Fi range, it's not unfortunately just as simple as using that formula before to calculate it. You're dealing with things of signal strength, signal to noise ratio, objects that are attenuating things, dealing with reflections and multipath in the environment as the signal bounces off of stuff, the frequency you're being used. But one of the most important things to keep in mind here is that Wi-Fi is two-way communication. Your access point or router is transmitting to your mobile device, your phone, your laptop, whatever. And then that device is having to send a signal back to the access point. And you will find here that there are some pretty significant differences in the output power of something like an access point versus your mobile phone. So a typical access point is, I'm using milliwatts here just to sort of highlight just how big of a difference this is. And because again, milliwatts sort of, exaggerates things a bit, but a typical home router or access point is probably somewhere in the neighborhood of 400 to 500 milliwatts. However, your typical consumer phone, even a flagship phone, is probably maxing out somewhere at 25 milliwatts as far as how strong that signal is. So it doesn't matter that your phone can see that signal from really far away if your access point doesn't have the ability to pick up the signal being sent back to it. Right? So you're dealing with TCP/IP, you're dealing with some other standards there, and there is handshaking. This device sends a bunch of data, and it waits for this device to receive that data, check that the data wasn't corrupted somehow and transmit, and confirm that it received the packets and it's time to send more data through it. So if this access point can't see those acknowledgments from the client device, you're not going to have a good conversation. So again, going with an analogy here, we'll go back to having a conversation with somebody. They have the ability to shout, but you're like me, you've got throat problems, you are not capable of shouting back. In fact, maybe you're talking in a bit of a hoarse whisper, right? That's going to change how far away you can be from that person to be able to have a two-way conversation. It doesn't matter that they can shout really loud if you can't shout back just as loud for them to hear you. Moving on here, RF behavior. So some things here to keep in mind when it comes to radio signals. Radio signals, often called radio waves, behave very similar to waves in a pond. So basically you've got your device and generally you've got an omnidirectional antenna on it, which sends the signal out. And when it transmits, it radiates out as a wave in basically a circular pattern. Just like if you toss a rock into a pool of water, you will see the ripples radiating out. It's very similar when it comes to radio waves. And just like those waves that you would see in a pond, if they hit a hard object, they can bounce and reflect off of it. Depending on the shape of the object, they can hit the object and scatter, creating waves going out in different directions at different strengths based on the shape of that device. Something that radio waves can do that water waves can't is you can actually pass through solid objects to a certain extent, depending on what they're made of, will determine how much it degrades that signal. And you can also have the radio waves, similar to water waves, will wrap around physical obstructions. So what happens is you've got this nice, simple circular pattern radiating out, but as it starts to interact with the environment, things happen here. Signals bounce around, so you get what would be essentially echoes. You get problems with, maybe as it passes through this, you're getting it coming loud from up here, but it's coming through softer from over here. So you get all sorts of sort of weird behavior, which can cause problems with the reception. And we will come back to this in a few more slides here when we talk about multipath and MU-MIMO and some other technologies. Another problem that has plagued Wi-Fi for a while, at least up until Wi-Fi 6, was how it determines who gets to broadcast. So with radio waves, right, you only get to, each device has to take a turn broadcasting. If you've ever been on a road trip, you've probably run into that problem where You're out sort of in the boonies between two large towns. Both of them have radio stations operating on the same channel or nearby channels. And when you're in either city, you can hear your local radio station just fine. But when you get out to that middle land, out in the desert or out in the fields between these towns, you run into a situation where you're now within range of both radios that are broadcasting, and they start interfering with each other, and it causes all sorts of difficulties with trying to hear the station you want to hear. So that's the same thing that happens with Wi-Fi. If two or more devices broadcast on the same channel or nearby channels at the same time, it becomes difficult to make out what the signal that you actually want to hear, and it basically causes a collision and packets to be dropped. Now, 802.11 was originally created all the way back in the late 1990s. And at that time, there was never a sense of worry or a thought that we would have like we do today, where a typical home can have, if you've got some smart plugs, you may have, 30 or more devices all wanting to broadcast at the same time. And we weren't expecting people to be doing things like streaming video, where you've got devices that are nonstop transmitting. So back then, when they created the standard for determining whose time it is to broadcast, they came up with this simple flow chart here. Basically, if your device needs to broadcast, it listens to see if somebody else is broadcasting. If nobody else is broadcasting, then it goes ahead and broadcasts. If it hears somebody else broadcasting, it then uses a random number generator to determine how long to wait. It waits, and then it listens to see if it's its turn to send. And then, if it doesn't hear anybody, it can transmit. So this can create some issues in today's modern networking environments, right? So one of the problems you run into is you've got a lot of devices that are transmitting. You've got people streaming video or music, so they're constantly sending. So because this is all just based on a random number generator, you can run into situations where every time you go to send your packets, somebody else is already transmitting. So there's no coordination there. And you just have to hope you get lucky. And one of those times when you listen, you find a gap in the transmitting. So then you go ahead and transmit. But another problem you run into, again, if you've got a lot of devices on the network, a lot of active devices, is you may have multiple devices that decide to listen at the same time. Both will see that nobody is currently broadcasting, and both will decide to transmit at the same time, which results in a collision and those packets being lost. So this is one of the things that is one of the probably the biggest factors that comes into play when it comes to how many devices you can have on an access point. You'll look at data sheets and they'll have some ridiculously large number. They'll say, hey, you can have 128 devices connected. You can have 512 devices connected. Maybe they'll say you have 1,000 devices that you can connect to it. And in theory, that's possible. But generally in the real world, you're going to run into problems due to this long before you get anywhere close to maxing out the theoretical datasheet maximum number of clients. So this is more to do with the 802.11 standard and how radio waves work than it does anything to do with the hardware, whatever model or brand of access point or router you're currently using. So this is a huge factor in limitations. That's why if you're talking to us, you're talking to your sales engineer, we'll tell you, look, maybe we'll tell you you need to plan to have one access point for every 20 users, or we'll say, well, maybe you need one access point for 50 users. It depends on what sort of traffic you're expecting and things like that. But that's why, even though the data sheet may tell you can have 500 devices on there, it's because in the real world, you start running into problems here when it comes to airtime management and coordination, because there is no coordination in any version of Wi-Fi before Wi-Fi 6. And even if you're using Wi-Fi 6 radios, there's a good chance that you've still got non-Wi-Fi 6 clients sharing that spectrum that can't take advantage of the coordination of the airtime. So as I've mentioned before, if two or more devices decide to broadcast at the same time, because you've got a lot of devices on your network, it causes a collision. Another similar problem you run into is what we call the hidden node problem. So we've got our access point here. The old time Zyxel resellers will recognize that graphic of our old access points from about nearly 20 years ago, 15 years ago. Anyway, so we've got our access point, and this blue circle is the area it covers. So it's where it's transmitting its signal, and it's the area where client devices can transmit back and it can hear from. So we've got one device on one far end of this area, and we've got another device over here in the opposite direction. So again, what happens is the devices, before they transmit, listen to see if somebody else is transmitting. So what happens if you've got two devices that need to transmit, but they cannot hear each other because they're too far apart from each other, but your access point can still hear them. So what happens is both will listen, see that they can't hear anybody else transmitting, so we'll decide to start transmitting. And you will get conflict because the access point won't know which signal it should be listening to. And you've got some other physical stuff that goes on that causes those signals to distort and have issues. So you end up with drop packets again. So again, as you increase the number of devices on your network, you're increasing the likelihood that you'll run into this problem. But it's something that can happen with just as few as two devices, depending on where they are in relation to each other and to the access point they are talking to. The next thing I want to talk about here has to do with data rate versus throughput. If you've ever gone on Amazon and pulled up a wireless devices review, I will guarantee you will see people leaving negative reviews or degrading their reviews. They'll go, hey, this product said it's an AX1800. I ran speedtest.net. I didn't even get half of that speed that they were advertising. And that has to do with data rate versus throughput. Now, IEEE, from the longest time, has defined basically the way they measure speed using the IEEE standard is the total data that is transmitted between two devices. And that worked great as a measurement back in the days of Ethernet and a hardwired connection, where there's very little protocol overhead of the medium itself. They basically just send the data over it. So there's very little overhead. Unfortunately, with Wi-Fi, there is a ridiculous amount of overhead, right? You're trying to send data over radio waves in unlicensed spectrum where you have to deal with interference from other wireless devices, regardless of whether they're Wi-Fi or not, industrial noise, all sorts of weird things like that, as well as just physical characteristics of the environment itself. The fact that your signals are bouncing off of certain objects or getting absorbed by other objects, things like that. So in order to make Wi-Fi work, there is a ridiculous amount of what we call protocol overhead. So this is additional data that is sent, checksums and things like that, which make sure that if packets get deformed or lost or dropped, that it's detected and that data is then retransmitted to solve the problem. So what you will see on data sheets is this data rate based on the IEEE standard, which is measuring all the data being transmitted between two devices, including all of that overhead. So we generally call that the data rate. That's the speed you're going to see on data sheets. That's the speed you're going to see on Amazon listings. It can also be referred to, depending on whose documentation you're looking at, as the physical rate or the link rate. So throughput, as the term is commonly used by people, is usually something that is measured using a speed test with something like speedtest.net, Ookla, something like that. And it is taking data from one device, like a file, and transmitting it to another device on the network, and then recording how long it took to send that data to figure out the maximum speed. So it's only measuring the actual data in the file that is being transmitted. It doesn't take into account the additional data that's generated as part of the protocol overhead. So that right there is why you will see a data rate of, say, 1800, but people complaining that their throughput is not able to exceed 900 megabits. It's because you're not measuring that extra overhead, which is part of what's included in data rate. So that's why you will see it. So generally, when it comes to Wi-Fi, you're generally going to see a throughput of 40 to 60% of what the advertised data rate is when you do a speed test, and you're not going to see it get above that. And that's why. And then, of course, also there's the fact we're dealing with Wi-Fi. So who knows what else may be slowing down that signal? Who knows what noise might be in the environment? Who knows what other devices may be transmitting at the same time they're doing this speed test? So there's a bunch of environmental factors on top of that, which can degrade this or can lower the speed. Another thing we'll be talking about here is spatial streams. Part of the way we get to the speeds that we do is by having multiple spatial streams. So maybe your router is capable of transmitting 4 streams at once, but your phone is only capable of listening to 2 streams at once. So that right there is going to have your speed, is going to reduce the speed by another 50% because you're only using your client device you're testing with is only capable of using half the spatial streams that your router or access point can support. Which leads us into how do we increase speed when it comes to Wi-Fi? Now, this is not about how do you in the real world optimize your network. It's about how is Zyxel as a manufacturer, as just the Wi-Fi standards go, how do we get faster and faster speeds over time? So the 3 main ways we're going to do it have to do with the encoding. How much data are we cramming onto those radio waves? So that's measured in something here called QAM, QAM. So 11N used 64-bit QAM. 11AC added the ability to do 256 QAM. And now with 11AX or Wi-Fi 6, we now have the ability to use 1024-bit QAM. So we've got higher and higher encoding levels that we can use to fit more data into the same bit of spectrum that we've got available to us. Now, in order to get these higher QAMs, the signal strength needs to be good. So one of the things that happens is if there's problems with the signal quality, one of the first things your device does, if it's noticing it's got problems talking, is it will reduce the QAM being used. So you're only going to be able to get the maximum QAM when you've got a good, strong, clean signal. So the next thing is spatial streams. You can increase the number of spatial streams that are being used. And I should have a slide coming up here where we talk about that a little bit more in depth. And then the other thing to do is we increase the amount of bandwidth that's being used. So when it comes to 11G, you had the ability to use 20 megahertz channels. A big chunk of the speed increase from 11G to 11N was that they doubled the amount of bandwidth that a single channel can use. So it went from a 20 megahertz wide channel to a 40 megahertz wide channel. 11AC allowed us to use 80 megahertz channels, and then 11AC wave 2 allowed us to use up to 160 megahertz channels. And that's still pretty much the widest channel we can use with Wi-Fi 6. So let's talk a little bit first off with bandwidth. So your 2.4 spectrum here in the United States is limited to roughly a 60 megahertz chunk of spectrum. And again, this is shared by any sort of wireless device operating in the 2.4 gigahertz space, other Wi-Fi devices, cordless phones, things like that. Most of your smart home products, whether they're Wi-Fi or a Zigbee or whatever, are going to be using this 2.4 spectrum as well. So the problem we run into here is even though if you pulled up the GUI in your access point or your router, you will see that you've got in North America 11 channels that you can use. Those channels are each 22 megahertz wide. So we'll just call it 20 to keep it easy here. So if your channel you're using is 20 megahertz wide, but there's only a total of 60 megahertz available, that means realistically, out of those 11 channels, you've only got 3 that you can use before you overlap with each other and can cause interference. Right? Channels 1, 6, and 11 are all you're stuck with to be able to use because anything else will overlap with one of those other channels. So again, part of the way we increase speed from 11G to 11N is we increase the channel size that we could use to 40 megahertz here. There's a typo up there. So you've got a 40 megahertz channel, but again, there's only 60 megahertz available for everybody to share. So the problem with these 40 megahertz channels in 2.4 is that basically you can only use one device, and any other device you use that's Wi-Fi is using 20 megahertz channels, and it's going to overlap with the existing 40 channel. And you obviously can't have 2 devices operating at 40 megahertz at the same time because you'll have 20 megahertz of overlap. So for a lot of homes, even if you've got a 11N device and you're using 40 megahertz channels, the device will probably automatically drop back to 20 megahertz channels to try to reduce interference if it detects another device. And that depends on the algorithm and the settings of the individual access point. It's not, that behavior is not set, but the original early devices that came out insisted on using 40 if you sent them to 40, and generally people in apartments and condos or houses that are close together had really nasty reviews because of the interference issues. So most vendors switch to an algorithm that tries to detect other nearby devices and will automatically reduce the channel from 20 or from 40 to 20. This is also why shortly after the launch of 11N products, you saw the first dual radio products hitting the market, where you've got 2.4 and support for 5 gigahertz. So why was that? It's because there's a lot more bandwidth available in the 5 gigahertz space. You've got, I believe, 26 non-overlapping 20 megahertz channels that you can use in theory in the 5 gigahertz spectrum, right? So you can have a lot more devices before you start running into interference issues with a 20 megahertz channel. Now, one thing I do want to highlight here is you will notice in this 5 gigahertz spectrum, there's this big section here that's highlighted in orange and yellow called DFS channels. So what happened here is the 5 gigahertz spectrum used to be a spectrum that required a license. So you have existing users using that 5 gigahertz space already with licenses that they paid good money for, and they had to pay to get their products certified and jump through all the hoops. So when the FCC decided to open this up for everybody to use, regardless of whether you had a license or not, there was a problem, which is, well, there's already people with licenses using this spectrum. So the FCC came up with this thing called DFS that basically says before an unlicensed user can broadcast in the 5 gigahertz channels that are part of this DFS spectrum that was already being used, you have to make sure nobody else is already using them, that is a licensed user. So that can be things like radar, weather radar being the most common. So if you're near a big city or you're near an airport, you probably have somebody using at least some chunk of that DFS spectrum. And there's other users of that 5 gigahertz spectrum as well that were using it previously. So because of that, you can't broadcast if you detect something else, but also after you've started broadcasting, if you detect a legacy 5 gigahertz user, you have to stop broadcasting. So to be able to use this DFS, it requires a little bit tougher implementation, and it can add up to 6 months for FCC certification to allow you to use those DFS channels. So because of that, a lot of consumer equipment doesn't support DFS. And even on the business side of things, oftentimes products will launch without DFS support, and then DFS support will be added down the road as a firmware upgrade. So you won't be able to use those channels until you upgrade the firmware. Now, the other problem you run into here as a business perspective would just be, again, if it detects a legacy user, you have to stop broadcasting. And, you know, it's very common for things like noise to look like a legacy user. And so your device usually errs on the side of caution and says, hey, we've got something weird going on here. We're going to stop using this DFS channel. So because of that, if you're using these DFS channels, you may see more disconnections than you normally would. And of course, if you've got users bringing products from home, there's a good chance one or more of your users is going to have a device that doesn't support DFS channels. So if you're going to avoid those DFS channels to get around those issues, right, you go from 26 non-overlapping 20 megahertz channels down to 8 or 9 non-overlapping 20 megahertz channels. So maybe there's not as much spectrum here as you originally thought. It's going to depend on your application and your users and how much control you have over them, whether you want to use those DFS channels or not. I can say from experience, the biggest problem you run into is just people bringing a device in that doesn't work. You know, we've had people call us and say, hey, we deployed your access points and Bob and Tina can't connect when they're in the conference room. What's going on? And we'll look and see, they're using a DFS channel on the IP in the conference room. And it just so happens to be the Bob and Tina's laptops don't support DFS channels, for instance. So anonymous attend me is asking, so it's basically better not to use them. Again, it depends on what you're doing and how much control you have over things. But in general, a lot of our people will choose not to use them, right? So again, if you've got a lot of users bringing their own device, you probably want to avoid DFS channels. Or it depends, it may just be that you'll just have to say, depending on the quality of service you want to provide, right? So if you're providing service, at a coffee shop, you might not care about those users. But if you are, say, hosting a conference room in a hotel, you probably want to avoid those channels because you'll have a lot of users that are bringing their own device, and you're going to have some that are going to have something that doesn't support DFS. And it also just depends on your RF environment. If you're worried about the disconnection issue, it depends where you are. If you're going to be running across that, we have people that are using DFS channels. I use them here in my house. I never have a problem with them being disconnected or having to change. Whereas at our office, I think it's probably due to industrial noise from one of our factory neighbors. We've had problems with it needing to change channels and disconnecting people because it's detecting a legacy user. And I suspect it's not actually a legacy user. It's RF interference from somebody's nearby industrial equipment. I think it's Chin Jen Wang is asking about a copy of the recording. So this is being recorded. It will be uploaded automatically probably by tomorrow to our YouTube page. It is Zyxel America channel, or Zyxel US channel is I think what it is. Either Zyxel US channel or Zyxel America channel. I forget. One of those is our YouTube. One of those is our LinkedIn. But it will be posted there. And I have given this webinar in the past. I do it about every other month. So you can also immediately today find a previous version of the webinar and watch the previous version of this. Okay, so back to this. So again, we were talking about before, the way we increase speeds has been doubling the bandwidth, right? From G to N, we went from 20 to 40 megahertz channels. So even if you are avoiding the DFS channels, you've still now got 4 non-overlapping 40 megahertz channels versus just 1 in 2.4, right? So again, you're able to deploy more access points operating on 40 megahertz channels. You can have 4 of them and not have any interference between them, right? So much better than as soon as you add a second one, you have interference. But again, we wanted to make Wi-Fi faster. So with 11AC, we introduced 80 megahertz channels. So now if you're using 80 megahertz channels, there's only 2 that you can use that don't interfere. So as soon as you add a third access point using 80 megahertz channels, we will start running into interference, again, assuming you're not using these DFS channels. And then we added with 11AC wave 2 160 megahertz channels. So for these products, to use 160 megahertz, you do have to use this DFS space. There is no way around it, but you're still now limited, even with DFS, to just 2 non-overlapping channels. So I think most of our business class products, even those that support 160 megahertz, I think our default setting is just to use 80 megahertz to get around the DFS issues and to get around the overlap issues. But most of our products will support 160 if you set them to use it. So I just wanted to make that clear here. So you can see how quickly a lot of spectrum gets eaten up as you're trying to get the faster speeds. So it may very well be in an AP dense environment that interference issues are the problem that you're dealing with the most. And it may be worth dropping from 80 to 40 megahertz channels to avoid those interference issues between nearby access points. So now we'll move on from there to spatial streams. So you may remember a number of slides back, I was talking about how RF waves can bounce off of things, they can reflect, they can scatter. So that creates something that we used to call the multipath problem. Your signal goes out and it physically is taking different routes in the RF environment, creating what is essentially an echo, right? You get into a room with a lot of hard objects in it and you shout, you hear echoes. And the reason you hear multiple echoes is because your voice is hitting different objects at different distances to you and then reflecting back. And it's the same thing here roughly with Wi-Fi waves. You can see in this example, the straight signal, right, is one distance, but the signal is also bouncing off of the wall and maybe some other objects in the room. And each of those paths is a different distance. So because they're different distances, you're getting an echo effect because that signal is coming in slightly offset due to the different length of time it takes for that signal to travel these different paths. So this is something we used to call multipath. And this was the bane of our existence in the 11BGA days. However, at some point here, people smarter than me figured out there's ways to take advantage of that. They built chips that were able to differentiate these signals that are coming in as basically echoes, and be able to filter those out. Those were the first days of this. And then somebody else even smarter came along and said, hey, you know what? We don't need to filter out those different channels. We can use those different paths being taken by the signal to send different data on each of these different paths. So these are what we now call spatial streams. So each of your antennas at this point now is able to transmit data on the same frequency, but different data for each antenna. And then the device receiving those signals is able to isolate the two signals because they're coming in at slightly different timings, and isolate them into two separate signals and then combine them together. So the most common way of doing this is on 2.4s. We have 150 megabit channels here. So you can basically, in the old days, you would have only been able to send 150 megabits at once. By taking advantage of multipath, you can create two streams at the same time using the same bandwidth and have 150 megabits of different data on each of those streams, so you can combine them together for 300 megabits total. So this is something that we would call MIMO, multiple in, multiple out. And this works that basically it's taking advantage of the fact we know these antennas are spaced apart differently. The receiving end will have multiple antennas spaced apart, and they're able to calculate the different distances that those signals are coming in, the different timing of the signals, even though they're being broadcast simultaneously on the same channel. So with 11AC, we introduced something called MU-MIMO, taking advantage of these spatial streams to send different data to different wireless users. So now what you can do is you can now do something that we couldn't do before, which is you could send data to two clients at the same time. Instead of having to send data to one client and then send data to the other client, you can now send data from your access point to two devices at once. However, it will be slower, right? So instead of a single 300 megabits amount of data being sent to one user, you can send 150 megabit streams of data to two different users. So with 11AC, this technology here was introduced with 11AC Wave 2, and it's only from your access point or router to mobile devices. The mobile devices, when they transmit data back, will still have to take turns transmitting data back. Wi-Fi 6 introduced the ability to then allow multiple users to send data back to the access point at the same time. However, some of the cheaper and or older Wi-Fi 6 chipsets do not support the multiple users sending data back. So when you're looking on a data sheet, particularly when you're looking at our documentation, rather than saying AX1800 or N450 or whatever on our business class products, we simply tell you how many spatial streams can be supported. So you will see something like 2x2 or 3x3 or 4x4. The first digit is telling you how many spatial streams the device can transmit. And then the second one is telling you how many devices, or excuse me, how many spatial streams you can receive. I think that's right. So when it comes to or maybe it's the other way around, I'm trying to think here. Anyway, sorry, I'm having a bit of a senior moment here. But anyway, so generally, when you're looking at business class access points, it will be the same number. You'll see 2x2 or 3x3 or 4x4. However, when you look at client devices, your phone, your tablet, your laptop, it's very common for these numbers to be different. What you're going to see is you may see a 2x3 or a 1x2. So that first number is the transmit number. So what it's telling you is if you see like a 1x2, is it can receive two spatial streams and combine them together. But when it transmits back to your access point, it can only send one spatial stream back. So it's basically able to send data back at only half the speed it's able to receive the data from. So again, it's something you see a lot on client devices. So you'll often see, business class access point supports 4 spatial streams, but your laptop may only be able to receive 3 at a time, and it may only be able to send back 2 at a time. So you're not fully optimizing the amount of bandwidth being used, the amount of data that's being sent. So you end up using more airtime to send the same data because of that. So that's something else to keep in mind when we're measuring speeds here and dealing with how many devices you can fit on the network is, different devices are going to be much more efficient at using that based on how well they match to your access point or router that they're communicating with. Now, if you, on some products, specifically primarily Cisco products, you will see something like this down here, 4x4, and then followed by a different smaller number such as 3. So the rules here, right, is you've got 4 transmit antennas, 4 receive antennas. So you think you've got a 4x4 spatial stream. But actually that number afterwards here, that 3, is telling you can actually only use 3 of those at any one time. So it's something which causes some confusion because people will just look at those first 2 numbers and go, hey, this is a 4x4 device. But in actuality, you've only got 3 of those that you can use at a time. And in theory, you could switch to whichever 3 offer the best, signal to noise ratio. But that's something you'll see a lot, like I said, on Cisco products in particular. So just to put this all together, right, the maximum speed you can achieve is a combination of how many spatial streams you're currently using, how many QAM you can receive, which has a combination of dealing with the technology, what's the max QAM that the technology supports, and then depending on signal quality, it may reduce itself from there, and then how much megahertz you're going to see. So anytime you're looking at a data sheet and they're talking about the maximum speeds, they are assuming the maximum number of spatial streams, the maximum QAM, and the maximum channel usage. So again, if you look at just a cheap 802.11 AC product, you will see it advertised as AC 900 because the maximum speed with all of those being best is 866. But let's say, for instance, here, you can't use 160 megahertz channels because your device doesn't support DFS. So you can see here that drops our maximum speed from 866 to 433. And then on top of that, you've got the protocol overhead, which are going to cut it, in half again from there as far as the speed test goes. So you can see how quickly here, even though we're advertising it as essentially a 900 megabit product, you're only going to get 200 to 250 throughput in any sort of speed test. So now we'll go back here to how many devices can you get on one access point. So again, there's no way to know. It is so much to deal with just the protocol itself and the environment and the type of data and users you're getting. If you're talking about like my home here, I've got a bunch of Wi-Fi smart devices. I can get a lot onto an access point because they aren't actually sending much data. Where if I had that same number of devices and each of those devices was streaming from Netflix and YouTube and TikTok, right, I wouldn't be able to get as many on there because they start interfering with each other because there's just not enough airtime available. And because, as we talked earlier in today's presentation, the ability that, or the technique that Wi-Fi uses to determine whether or not you can take your turn transmitting isn't very efficient and isn't optimized for today's modern environments with a lot of active users. So in general, the issue is going to be the technology being used. Is it an AC clients or the 11N clients or the Wi-Fi 6 clients? How many spatial streams these support, et cetera, et cetera. So you're going to hit your limit realistically long before you get anywhere near what is on that data sheet. And in most environments, it's not going to make any difference regardless of what's on that data sheet. And that data sheet isn't anything having to do with really the capability of the hardware itself or the implementation. It's just how much memory they have allocated to storing those entries in theory. So we'll give you sort of a real world example here. So we are simulating here a number of users that are using a stream. So they are each using a 3 megabit, call it a video stream here. So you've got an access point here that supports 3 spatial streams in both directions. And you've got devices here. You're using laptops. This is an office environment, so you control the devices being used. So you've got laptops that support 3 spatial streams. And you can see here, we're able to fit 34 laptops on there, each with that 3 megabit stream, giving us roughly 77% airtime utilization. We're going to change that now to a tablet, and we're going to assume everything else changes or is exactly the same. The only thing that's changing is the number of spatial streams. So we're going from a device that supports 3 spatial streams to a device that only supports 2 spatial streams. Again, still doing these 3 megabit streams that they need. And you see we go from 34 devices that we can fit on that access point to now we've only got 21 devices that can be used at the same time. As soon as you add a 22nd device, you'll start getting interference issues. Take away another one of those spatial streams, you're using a device that only supports 1 spatial stream. And now you can only support 10 users using 3 megabit streams, assuming signal strength and everything else is exactly the same. So that's just showing you here, and we'll just go here, the aggregated throughput goes from 100 megabits with 3 spatial streams to 65 megabits with just 2 spatial streams to just 30 megabits with 1 spatial stream. So that's just one factor we're looking at here, which determines how many users you can have on that network before you start running into issues. And again, the only thing we changed here was the spatial streams supported by the client device. You start throwing in other real world issues here, right? Some users are using AC, some users are using Wi-Fi 6, some are using N. That's going to affect things. The comparative signal strength of those users is going to affect things, right? If some of these users are farther away, you're not going to be able to connect it as fast as speed, so you're going to require more airtime to transmit the same amount of data. But just showing you here just how variable it can be with the exact same usage scenario and signal strength scenario. So what is causing that? Again, we talked about before, when it comes with Wi-Fi, ignoring multi-user MIMO and some of these other technologies, in general, each device has to take turns transmitting, and only one device can transmit it at a time. You are sharing a bunch of space, not only with your other nearby neighbors' access points, but with any other sort of wireless device, because they're all using that same spectrum, as well as just interference issues being generated by non-wireless products. You know, the most famous example here is a microwave in your house is using the same 2.4 frequency to heat your food as your Wi-Fi is using, that your Bluetooth is using. So if your microwave shielding isn't up to par, you may get signal leaking out of your microwave, which can cause interference with your other 2.4 gigahertz stuff. Business equipment does not have to follow the same FCC rules as consumer equipment. So it's very common for industrial equipment to put out RF interference on all sorts of channels. Could be 2.4, could be 5, could be both at the same time. It just depends. So we'll take a look here. How do you normally deal with co-channel interference between access points? So you've got multiple access points. You're trying to use the maximum amount of channel bandwidth as possible for the fastest speed, so you've got some overlap. Now, the traditional way of dealing with co-channel interference is by turning down the power. So you turn down the power of your access point, so the access point strength is much more closely matched to your client device strength, right? We talked about before, right? There's a huge difference in power output between your access point and your client devices. So your access point is sending that signal a lot farther than it needs to. So you reduce the power output and you reduce the interference between those devices, which is good. The downside to that, though, is because you're reducing your transmit power, is you're now worsening your signal to noise ratio on your client side. So it's not going to harm anything as far as the signal coming from your client device to the access point. But I think in most scenarios, it's quite normal that you're sending a lot more data from your access point to the clients than vice versa, right? You're much more likely to be downloading files onto your computer rather than uploading them. You're much more likely to be downloading web pages. You're much more likely to be streaming video or music or audio from the access point to your client rather than the other way around. Some questions have come in, so let's hit those questions here. Anonymous attendee is asking, is there a way to create multiple SSIDs and somehow segment these different devices to help overall throughput and reliability? Multiple SSIDs isn't really going to affect things. In fact, multiple SSIDs can make it worse. So even though you've got different SSIDs, they're still going to be connecting to the same radio, right? So most devices have one radio that's working on 2.4, another one's, and you've got one radio operating at 5 gigahertz. So all of your 5 gigahertz SSIDs are still going to be broadcast from that same radio. So it's not going to help as far as segmenting your traffic. As far as SSIDs go, and in fact, if you're running multiple SSIDs, you're using more airtime on the AP side of things because it's having to broadcast out the connection information for each of those SSIDs. So it's not a lot of extra data, but it is a little bit extra data that can hurt performance. So no, extra SSIDs won't help things. One way to do it, like for instance, in my house, stuff that doesn't matter about signal quality, so like my smart home stuff, my Google Home Assistants, things like that, I have those connect to a 2.4 radio. And then I reserve my 5 gigahertz radio for stuff that needs a lot of bandwidth. So for instance, I have a VR headset that's wireless and I can do wireless streaming from my PC to my headset. Works pretty well, but so I have that on a 5 gigahertz radio that I only use for that. So I'm not sharing that radio with any other 5 gigahertz or 2.4 devices in my home to make sure I have no drop packets, because drop packets are a huge problem when it comes to streaming VR. So that's one of the things you can do there. RW is asking about solar panels causing interference. I am not familiar with solar panels putting out noise. I mean, the solar panels themselves wouldn't. You ask about blocking, and it may very well be Wi-Fi signals would block it, but I don't think you're going to be in a situation where you're trying to send signals up through solar panels to another wireless device. So I don't think that would be an issue there. You may have issues, though, on your inverters, right? You may have inverters up there. Those are taking the signal, they're taking that DC signal that's coming in and then combining them together, and then you send them to a central inverter, which then converts them to AC. So those may put out RF noise. I haven't heard anybody complain about it, but it's very possible depending on the model, how good the shielding is, if it's properly grounded and things like that. So those may be the issues, but I wouldn't think the panels themselves may cause an issue. So Anonymous was asking how multiple SSIDs create more problems. So I think I explained that already, but I'll just go ahead and hit that again just in case I didn't. And that is that basically for each SSID you have, your access point has to broadcast and let people know that, hey, this SSID exists. Here's its settings. So that's some extra packets that have to be sent. So it's just increasing the amount of data that's having to be transmitted from the access point. It's not a lot of extra data, but it has been known to cause issues when you've got a really heavily overwhelmed access point to begin with. Yeah, so Doug is saying that he's dealing with clients in all metal, where they have metal walls, ceilings, and stuff like that, and there's a lot of attenuation. So yeah, so generally, metal is going to block signals. It's just the way it is. And solid metal reflects the signal. So what you're probably seeing is an attenuation, because you're probably not sending that signal through those walls. But what you're probably seeing is you're getting a lot of that signal is hitting those walls, it's hitting those girders, it's hitting those beams, and it's reflecting. So you've got a lot of multipath or echoes, essentially, which are causing a lot of packets to get dropped just because it's causing too much interference. We talked about before, we were able to take that multipath and create, MU-MIMO and stuff like that. But when you've got a lot of, you've got too much reflections, you've got too many different paths going on, it can overwhelm the Wi-Fi chipsets and make it very difficult for them to be able to distinguish the signal they're trying to hear versus all those echoes coming in. Anonymous attendee is also asking here a cost benefit to separate 2.4 and 5 gigahertz more on what you discussed. So as we've talked about earlier today, you've got a lot more bandwidth available in 5 gigahertz. So with 5 gigahertz, you are able to have more devices operating, more access points, we'll put it that way. You can have more access points in an office, for instance, or a warehouse, operating on 40 or 80 megahertz channels without interfering with each other, because there's more channels, so you can choose non-overlapping channels. Where with 2.4, you're stuck with 20 megahertz channels to avoid interference. And even then, you've only got 3 that you can use, right, before you have interference. So it's very common to have interference issues on 2.4. So one of the things you want to do is you can move your clients that don't need lots of bandwidth, or that don't need are using applications that don't really care about signals or packets being dropped and retransmits and stuff like that. Move those to 2.4 and then reserve your 5 gigahertz for those devices that do need it. And then further, depending on your environment and your application, you can segment it so certain access points in your environment on using one set of channels, are reserved just for those high maximum throughput applications you need. And you can still have other access points using different SSIDs on different channels for your rest of your devices that can use 5 gigahertz, maybe need a little bit more bandwidth, but aren't so sensitive to drop packets. So what we're talking about here, let's just use an example here, voice over Wi-Fi. So voice over Wi-Fi is one of the hardest things to do out there. People want to do it, right? Because it's cheap, it's free. You can use your existing VoIP infrastructure. But the problem with voice is, even though it uses almost no bandwidth, right? It's only using, maybe 54 megabits per second, maybe, 1,000 or, maybe 124 or something like that, and the maximum. You don't have a lot of bandwidth being used or data being sent to do voice. But the problem with voice, and this is also true with VR, is the problem with voice is you can't buffer that signal, right? Because it introduces too much delay. We all know that horrible thing when you call into a VoIP conference call and you have that lag, right, between when you speak and the other people hear you, so you end up talking over each other. That's caused by buffering. Because some of those packets are going to get dropped and need to be resent, even when you're on a wired connection, and if you're going out over the internet. And then you throw in Wi-Fi with all these problems that we deal with Wi-Fi. So you get a lot more drop packets. So there's a minimal amount of buffering that you need to have. So if packets get dropped, they can be retransmitted, and then what you're talking about gets combined back together so it sounds right. If you buffer too much, there's too much lag or delay. So it's hard to have that conversation because you end up speaking over each other. But if you don't have enough buffer and those packets are getting dropped, you don't have enough time for the resent packets to get there and be reassembled. So you start getting drops in the middle of what people are saying. So I'm sure we've all been in that thing on a conference call or whatever, where somebody's talking and it's like dropping out in the middle of the words they're saying. That's caused by packets being dropped. So that's one of the problems here when it comes to Wi-Fi, is you introduce a lot of opportunity for packets to be dropped. So that's why it's one of those things where if you are doing voice over Wi-Fi, we will tell you, limit the number of clients that you have per access point to something really small. Maybe as low as 16 devices at max per access point to try to work around this. So same thing with VR. VR, you need to react in real time. If there's too much delay, you can get motion sick really bad. So there needs to be almost no delay, almost no transmit. So you'll want an access point or an SSID that you're on, so it's not competing with anything else that may cause those packets to be dropped. Hope that answers that. There's 2 other questions here from Anonymous. I am going to get to those later so we can finish on with this topic. We'll answer these ones here towards the end. I will come back to them, I promise. So as we talked about here, generally most access points that you're dealing with have a sort of round antenna or have a signal that goes out in roughly a circle radiating out from wherever the antennas are. In the cases of outdoor point-to-point equipment, you've generally got a directional antenna, which focuses the beam in one direction. So there's a technology out there that we have, that Ruckus has, and pretty much just that, called smart antenna. Ruckus calls theirs BeamFlex Plus. So smart antenna is a really good way to deal with co-channel interference. So the general idea behind smart antenna is instead of having one fixed antenna pattern, you have hundreds of different antenna patterns possible, and the access point chooses the best antenna pattern to focus the signal to where the client is in relation to the access point. Now, we've gone a step further with the algorithm we use, and we choose not only a pattern that's designed to focus the beam as much as possible towards where the client device is, but it's also specifically designed to ignore sources of interference. So it's not listening in those directions where interference may be coming in. So smart antenna technology is not beamforming. It is its own separate technology that's much nicer than beamforming. It's able to work with any client device. The client device doesn't need to support it. And smart antenna works with users that are moving around, whereas beamforming and some of the other technologies out there are incapable of dealing with clients as they move. So we'll give you a real world example here. So this is a hotel environment. These are using small, low-powered access points in each room. This is very common these days in most of your mid-tier and higher, newer properties, rather than the old way of putting an access point in the hallway. We'll talk a little bit more about that later, why it's moved to this. But anyway, we're using 5 gigahertz channels here. So there is some channel overlap, but you can see there's because we've got 5 gigahertz here and we're using, I think, 80 megahertz channels. We've got a number, we're not having anybody be directly next to anyone else. As you can see here, we've got 2 APs spaced apart from each other on one floor and another AP on the same channel on the floor above it or below it. So what we got here for the test is we have our NWA 1302. We no longer make it. Similar hardware to the 5302D-S. And the Ubiquity UAP AC IW. Similar form factors, the same 2x2 11 AC technology, similar power output. The only real difference between these two products is that smart antenna technology. So we have one AP turned on, and we had multiple clients, and we aggregated their throughput. So what we saw is we get an aggregated throughput here of roughly 400 megabits across both devices. In fact, the Ubiquity slightly faster than us in this environment. When we look at airtime utilization, we see it is 67% between the two products. So the same airtime utilization. So 100% is the theoretical maximum airtime utilization you can get to. But as we talked about before, prior to Wi-Fi 6, there was no coordination. So you never get 100% airtime utilization. There's always some loss there. So now with 2 APs going on, we redid the same test, aggregated throughput, and what you see between the 2 APs, the Ubiquity goes up to 555 megabits per second, but we get an aggregated throughput of 785 megabits per second. And you will also notice here that the speed between the 2 APs is roughly the same, whereas with the Ubiquity product, and this would be true of any non-smart antenna product, even ours, you will see that the airtime or the bandwidth is very different. One of them is getting 400 still, the other one is only 221. So if you look at airtime efficiency, the Ubiquity 2 APs get up to 95% airtime efficiency between the 2 access points. But because of smart antenna, we can exceed the theoretical 100% maximum airtime utilization and get up to 131% airtime utilization. So because this smart antenna is basically allowing us to ignore some of that interference that's going to happen between those 2 APs, we can exceed the theoretical maximum airtime utilization. And on top of that, the smart antenna allows us to much more evenly distribute that airtime between the two access points. You get very similar performance between the two. So if we go up to 3 APs now, all operating on the same channel, but physically spaced apart from each other, they're all several rooms apart from each other, one's on a different floor, we see that same thing. The aggregated throughput, I think I'm missing the aggregated throughput numbers, but the aggregated throughput continues to increase across those 3 APs. So now we're up to 900 megabits aggregated between the smart antenna APs, where if we go to the non-smart antenna APs, the aggregated throughput is actually dropped from when we go from 2 to 3. And we see here the reason for that is, again, airtime utilization. Because of the increased interference and the retransmitting and stuff, airtime utilization drops to 91% on the non-smart antenna AP. But on the smart antenna AP, we're up to now get up to 155% of the theoretical maximum airtime utilization. And again, it's the smart antenna doing that by allowing us to reduce interference, even though we've got multiple devices within range of each other operating on the same channel. So that's it for smart antenna. So now we'll start talking about some more general stuff. There is one more bit of technology I do want to talk about here, and that is our dual optimized antennas. So you see here again, the typical access point is designed basically to be mounted on the ceiling above the area that's being covered, and it covers a roughly circular area underneath it. However, in the real world, we don't always get to mount our access points on the ceiling. Oftentimes we have to mount them on the wall. So when you do that, you end up sending a lot of that signal into the floor and ceiling where it gets lost. Or if you've got thin floors, you may cause interference with the floors above or below you. So we have something here. I guess I'm missing the slide I thought I had here. We have something that we do offer on our products called dual optimized antennas. As far as I know, we are the only vendor that offers this. So some of our APs have smart antennas, some of them have the standard antenna, and some of them have what we call this dual optimized antenna. And basically, instead of having the standard single antenna pattern, we have 2 sets of antennas built into the access point. One that's optimized for ceiling mount and one that is optimized for wall mount. And then we let you choose on a per AP basis which antennas to use based on where you've mounted that device. So if you know you're going to be mounting some stuff where you probably shouldn't, it may be a good option for you if you can't afford the smart antenna technology. So just in general, antennas should be mounted on the ceiling, and you generally want them to be as high as possible over the area to be covered. Now, within reason. And the reason I'm saying here within reason is, obviously if you've got some ridiculously high ceiling, if you mount them up there, your signal is going to travel a lot farther than it needs to. And also that antenna panel, like I said, it's circular and it's spreading out. So it may spread the signal out more than you ideally want it to be based on where other access points are. But the general reason why you want it on the ceiling is, one, the antennas are optimized to be mounted on the ceiling, but also by putting it up on the ceiling and putting it up high, it reduces the amount of obstructions that are going to be between your client and that access point, right? So ideally, you want that signal to travel through clean, free air between the access point and the client. You don't want it having to travel through cubicles or columns or people walking around, things like that. So one thing we run into, which is a common question, which is, most businesses have some form of drop ceiling. But oftentimes your customer is like, I don't want you poking holes in my drop ceiling. So if your local building codes allow it, you can oftentimes just set the access point on top of that drop ceiling. Your typical standard acoustic drop ceiling has very little attenuation. They're mostly made up of basically cardboard. So it doesn't really attenuate the signal at all. So you can simply set the access point on the ceiling pointed down, and that's just fine. Again, if your building codes allow it, some places will not allow that because that's your plenum space. Some of our APs are plenum rated, some of them are not. So you have to take a look at that. One other challenge you get into oftentimes if you don't have a drop ceiling or you're trying to mount above the drop ceiling is that your ceiling has all sorts of nasty metal things on it, right? You've got pipes, you've got conduit, you've got AC venting. So all of those things are metal. All of those things can block or reflect signals. So generally you want to try to keep your access point away from anything that's metal that could cause issues up on that ceiling. So a lot of times if you go into big conference centers and things like that, expo spaces, you will see the access points are actually mounted onto poles that drop from the ceiling. And that's done to avoid those other obstructions up there, as well as to minimize the area being covered by each individual AP, because generally in an expo center, you've got a lot of access points in the same area. So when it comes to hotels, the standard way of providing Wi-Fi in guest rooms for the longest time was to mount the access points in the hallway and then provide coverage to multiple rooms at the same time. I have seen hotels do as few as 1 AP per every 16 rooms, or or at least 1 AP per 8 rooms. I have seen this, and basically as time has gone on, Wi-Fi utilization has changed, and that no longer works for a lot of your hotels. And some of this will have to do with how the hotels themselves are designed. So for instance, in a lot of hotels, the room that borders that wall is usually the bathroom, right? So the bathroom has got tile on it that's going to block signal. It's got pipes, it's got sinks, it's got mirrors, all these things that block the signal. So it's hard for the signal to get through that into the room. And depending on where that AP is in relation to where the guest is, that signal may have to travel through 2 guest bathrooms before it gets to the area where the user is. And then as we talked about before, your clients are bringing in their own devices. So their, $49 Walmart special tablet probably doesn't have a lot of signal strength and may not be able to get the signal back out to where that access point is. And then also just how we're using it's worked, right? It used to be you would have, one guy that has his laptop checking emails connecting to that hotel Wi-Fi. Now you may have, their phone wants to get on the Wi-Fi, their laptop wants to get on the Wi-Fi, they're streaming Netflix HD. So your AP is handling a lot more traffic and users than it used to in the old days. So what we have seen at this point is that most of your mid-tier and higher hotels are getting away, especially newer constructions, are getting away from APs in the hallway and instead putting 1 AP per room or 1 AP per every other room. And all the major vendors now have APs specifically designed for this in-room hotel usage. So they're a small, lower powered access point that's designed to mount directly to a wall plate in the room. So that's what we're seeing a lot more of as far as in-room goes. And in general, if your AP has visible LEDs, you want the ability to turn those off, right? Because no one wants a flashing green light lighting up the room when they're trying to get to sleep and dealing with jet lag. So when it comes to more public areas, the main thing you're going to build for isn't necessarily going to be the size of the space, but how many users are going to be in that area. A lobby may just need 1 access point if it's just a lobby where people are checking in. But if this is a lobby that also has a large area for guests to sit in, that has a number of tables or desks for people to work at, you may need more APs based on how many users you're going to have in there. And in general, you wanted to divvy up and design the Wi-Fi coverage based on the individual room and its usage. So you would have, 1 set of APs for the lobby, 1 set of APs for the conference room, 1 set of APs for the hotel bar, et cetera, et cetera. For these public areas, you're going to want to turn on load balancing and client steering to help distribute those users over the available APs in the area. And again, you want to design this for the individual area. So you don't want to be load balancing between the lobby, and the hotel restaurant or something like that. So you'll create their own little zones and load balance between them. In any area where you've got either a large number of users or a large number of access points, use smart antenna. It makes a huge difference in these dense RF environments. When it comes to schools, it depends how those rooms are being used. So, you got to ask yourself, how many students are in this room? Is each student going to be using a Wi-Fi device, a Chromebook, a tablet, something like that? In the art classroom, they may not be using their tablets, whereas in their, social studies classroom, everybody may be on the tablet. And then, or it may be one of those situations where they're only on their tablets for 5 or 10 minutes at the end of class for doing their own research, versus a smart classroom where the teacher is streaming video onto every single student's device, or is mirroring the whiteboard onto every student's device. So you have to look at, how that network is being used and deciding how many students are going to be on there. In general, if it is a room where students are going to be using tablets for most of the time, there's screen mirroring going on, we would suggest that you use one AP for every student. And if there's going to be 30 or more students in the room, we highly recommend using smart antenna technology. So now I want to talk a little bit about Wi-Fi 6 and Wi-Fi 6E. So Wi-Fi 6 is still relatively new. There is some confusion on it, so I do want to hit on some of this here. Wi-Fi 6E was designed to solve a lot of these problems I talked about in the first half of today's presentation. So it was the first really sort of ground up rework of the Wi-Fi protocols to solve a lot of the issues we have, specifically dealing with high density environments. So again, high density could be a lot of users on one access point, or it can be a lot of access points in the same area, generally because you've got a lot of users on them. So it was specifically reworked to deal with these sort of environments and help solve them. So there is some technology that makes that possible. OFDMA better lets you segregate up chunks of the available air spectrum, the ability to have upstream MIMO, and some other technologies like that. So one of the problems we run into here is Wi-Fi 6E Wi-Fi 6 wasn't actually approved until last year, but there have been products on the market calling themselves Wi-Fi 6 since at least 2020. So a lot of those early products that came out, the hardware itself doesn't support all of the features that are part of the Wi-Fi 6 standard. And in fact, the Wi-Fi Alliance didn't add support for some of these common features until just this year. So products that are Wi-Fi 6 certified that launched last year are very likely missing some features. And then on the lower end products that you run into, they may be using older chips or some of these newer, cheaper chips that either don't have these features or the implementation doesn't work that well. So when you're out there, not necessarily all Wi-Fi 6 products support the full Wi-Fi 6 feature set. So we like internally and on our marketing materials we like to call our lower end sort of consumer products Wi-Fi 6 Lite. However, we're the only vendor using that. Most other vendors don't differentiate between full Wi-Fi 6 features and what we would call Wi-Fi 6 Lite. So some products that are out on the market are missing some of the Wi-Fi 6 features. So we give you an example here between the Gen 1 Qualcomm chips and the Gen 2 Qualcomm chips. You can see upstream OFDMA and upstream MIMO are not supported, as are some of the other technologies here like TWT and BSS coloring. So it's something to keep in mind. Also, some vendors, Wi-Fi 6, I forgot to mention this on the previous slide, Wi-Fi 6 is the first new technology since 11N for the 2.4 gigahertz radio. So if you have an 11 AC device, that AC technology is only on the 5 gigahertz radio. The 2.4 gigahertz radio is still 11N. So with Wi-Fi 6, you have the ability to add Wi-Fi 6 technology to your 2.4 radio. But some vendors, for instance, the Ubiquiti's lower end Wi-Fi 6 products only offer Wi-Fi 6 on the 5 gigahertz radio. The 2.4 radio is still the older 11N technology. So something else to keep in mind. So when it comes to our products, all of our Wi-Fi 6 products are Wi-Fi 6 on both radios, 2.4 and 5. And anything that's our business class product. So that's basically any of our access points that have at least 3 digits in the model number. So the 110 and higher, those all are the full Wi-Fi 6 feature set. It is only our 2-digit NWA 50, 55, and 90 products that may be missing some of the Wi-Fi 6 features on them. And that's just something we have to do to get that lower price point that we offer those at. It was weird. I got a weird pop-up here. Sorry about that. So now let's talk about Wi-Fi 6E. So similar to how, back in the 90s, the FCC decided to open up this licensed 5 gigahertz spectrum for unlicensed use. The FCC has now done the same thing with 6 gigahertz technology. So 6 gigahertz is a new chunk of spectrum that recently opened up for people to use. Now, the benefits of 6 gigahertz here are 2.5 times more capacity than 2.4 and 5 gigahertz combined. So it allows you to have 160 megahertz channels, and you can have 7 of them that don't overlap. And as far as I know, there's really nothing else using 6 gigahertz indoors. There's no Bluetooth, there's no Zigbee or anything like that using 6 gigahertz. So the only source of interference is other Wi-Fi devices or industrial equipment. So this is sort of a breakdown here of the different channels here. So you can see massive amounts of spectrum. So we go from 5 gigahertz having 260 gigahertz channels to now having 7 of them available for you to use. So you've got a lot of spectrum to play with, so you don't have to worry about interference between other devices in the local area. Now, some of the problems when it comes to Wi-Fi 6E is this 6 gigahertz spectrum was already being used by other sources. Specifically in this space here, it is television broadcast crews. So those remote crews are using 6 gigahertz to send their signals, and utility companies use 6 gigahertz to send signals back. So because of that, they have a technology similar to DFS, but in theory better, that's going to be required to be used on any outdoor 6 gigahertz products. The problem you are running into here, though, is the FCC still hasn't released the rules for what needs to be done for outdoor. So right now, it is illegal to use 6 gigahertz products outdoors. You can only use 6 gigahertz products indoors. And there are a number of lawsuits currently trying to block outdoor implementation. So I have no idea when 6 gigahertz will be allowed to be used outdoors. We had to cancel our outdoor products because we're still waiting for that to get worked out. So 6 gigahertz can only be used indoors. The other problem you run into on this is that it's higher frequency, it's also lower power. So higher frequency reduces your range, lower power reduces your range. So you're going to get much less coverage on 6E 6 gigahertz connections than you are on 5 gigahertz. So for instance, in my house, I have a smart antenna access point, and it's located roughly in the center of my house. I can go into any room in my house and have a decent, reliable 5 gigahertz connection. That is not true with my 6E connection. I have difficulty just 1.5 rooms over from the access point because it's getting absorbed by the walls and just the air in general. So that's something else to keep in mind. We see similar complaints on consumer reviews on Amazon and places like that. So that is something to keep in mind. 6 gigahertz does not travel particularly far. The other problem you run into with 6 gigahertz, right, is to support it, you need 6 radios. So you're paying for an extra radio, an extra set of antennas, and you're also paying for a much more powerful processor because you've now got to process a lot more data than if you just had 2 radios. So you're essentially, by adding this 3rd radio, which is you're in theory, adding a significant amount of overhead to what needs to be done. So because of that, 6E products tend to be expensive. One way we have dealt with that ourselves internally is we have launched some lower price 6E products that are only dual radio. So you can choose to use the radio for either 5 or 6, but you can't do both at the same time. So this is more of a way to add 6 gigahertz to an existing network by just adding some new access points where you want that 6 gigahertz coverage, or for future proofing your network. right now there are not a lot of 6 gigahertz devices, client devices on the market. So you can roll out your APs using 5 gigahertz today, and then at some point in the future, once you've upgraded everybody's equipment to support 6E, switch over to 6 gigahertz. In general, though, the main areas where you would want 6 gigahertz are high density environments, right? Because you've got all these extra channels, so you don't have to worry about getting interference from your neighbors or from access points a couple rooms over. And this is one of those areas where the weak signal actually sort of benefits you there as well. And then also just for applications that require a lot of bandwidth or are really sensitive to interference and drop packets, such as streaming like VR. Another area where I think Wi-Fi 6E is going to be good is for doing backhaul. So you can use 6 gigahertz to backlink in a wireless mesh or a point-to-point scenario. In particular, outdoors, once the legal situation gets resolved when it comes to outdoor stuff. And that, guys, is the end of the presentation. I've got a lot of questions here, but if you have some questions, feel free to send them in using that question and answer interface. Real quick, most of our webinars that we do, both mine, Try's, Marcus's, get recorded and they do get uploaded to our YouTube page. If you search Zyxel, you get a lot of hits and a lot of channels and videos from other markets. So if you're looking for stuff that we have done here in the United States, Zyxel America channel is our YouTube channel, and that's where everything will get uploaded. And then you can find us on LinkedIn as Zyxel US channel. And now let's get on to the questions. Is there a benefit by excluding older BG devices, and to what degree? So yes, this is something that comes up a lot. You know, your older devices, you know, something that's using a previous technology, it doesn't matter what we're talking about. If we're talking about the difference between 11N to 11B, 11AC to 11N, Wi-Fi 6 to Wi-Fi 5, older devices are going to slow down your network. So, you know, sometimes what you do want to do is you want to say, hey, I want to block BG, or I want to block, you know, BGN devices because they're too slow. They're too inefficiently using my airtime. And, you know, unfortunately, if you've got a user that's still got a device that's using that older technology, they just won't be able to connect. But it can create a better experience for your other users. So will commercial building with irregular shapes and heights of metal ceiling plus tinted windows glass be an issue for Wi-Fi reception? So yes, it is. Anything metal is. Metal is the worst thing out there. Even non-solid metal, as far as getting the signal through it, is going to be really hard. So stucco, for instance, you know, if you're trying to get a signal through a stucco wall, it's hard, because the hole, even though there's lots of holes and lots of empty space, because of the size of the radio waves, they tend to always end up hitting that metal and getting absorbed by it. So yeah, metal is bad in general, but when you're talking about areas inside of a metal building, generally the issue you're running into isn't attenuation from the signal being blocked. It's that the signal is being reflected off those surfaces. So that always creates a higher noise floor. Whereas if you're in a building that's primarily concrete walls, the concrete walls won't let the signal go through them, but they also don't reflect a lot of that signal and will absorb it rather than reflect it back, where metal loves to reflect back. So you'll get a lot more reflection issues raising your noise floor in metal construction than you will in concrete construction. How do you limit the number of devices per access point? So we have those settings in our GUI. So if you go into the Nebula interface, we've got a number of different sliders and things that you can adjust. So you can adjust how many users your access point will allow before it will just start blocking people. You can also set a rule for minimum signal strength before it will block you. So it will automatically, so this is a problem historically. I don't know if it's still the case with modern iPhones, but your older iPhones and stay connected to the first access point they connected to, even when that signal became unusable, even if you were sitting next to another AP with the same SSID that had a beautiful, clear signal. So one of the ways to sort of force your client devices to roam is you can set a minimum signal strength in our settings. And as soon as that signal strength drops below that, we will disconnect that user, forcing them to reconnect. And hopefully they will reconnect to a closer AP with a better signal, rather than trying to maintain a connection to that AP that really is too far away to make it usable for them. And along those similar lines, something else I do want to bring up, and I forgot to bring it up earlier in today's presentation, a very common problem you run into is people are using the signal strength as shown on their phone or on their laptop as a way to judge the quality of the Wi-Fi signal. So with those bars you're seeing, you'll say, hey, I've got 3 bars of Wi-Fi, but my Wi-Fi isn't working. Why is that? What's going wrong here? And that comes down again to the problem we have where the signal coming from your access point is a lot stronger than the signal coming out of your client device. So your client device can tell you, hey, I've got a good strong signal from the access point, but it has no way to know if that signal is making it back to the access point. So your client device may show a strong signal, but that's telling you how strong the signal is from the AP. And it may be that your client device doesn't have the power to send a signal back to that access point. So that's a very common problem we run into, and something that people that are first doing a site survey run into is they just look at the bars. They don't actually check to see if they can transmit data or how reliably they can transmit that data. So you need to actually check when you're doing a site survey whether how good that connection is back to the access point. Best way to deal with local Cisco access points that seem to be able to block out, shut down other vendors' access points. Okay, so a common feature that you will find on some Wi-Fi products is what's called rogue AP detection. So with rogue AP detection, the idea behind it is to make sure nobody has plugged in an access point to a wired connection in your building and is operating an access point that doesn't comply with your security policies. So the idea behind this is, you can have your APs, and Cisco promotes this. A lot of Cisco APs have a dedicated radio. Its sole purpose is to find other nearby APs and try to block them. Now, in theory, it should only be blocking APs that are on your network, but they don't necessarily test for that. I don't know that I have a strategy for dealing with it, other than to say, maybe find out who's operating those networks and talk to them. There have been cases where people have, let me backtrack a bit. It is illegal in the US to interfere with another device using 2.4 or 5 or 6 gigahertz spectrum intentionally. So you can make the argument that if they are purposely using their rogue AP detection and containment to block access points that are not something that is on their network, that they are in violation of those FCC rules. There have been cases where people have been fined for doing this. I suspect it's not worth the time and hassle to actually go to court and try to prove this, but it may be worthwhile to contact whoever your neighbor is who is causing these problems for you and let them know that they are in violation of FCC rules. And to ask them to turn that feature off since they are interfering with access points on your network, not their network. Best advice I can give you on that. Yeah, so ceiling pointing down better than pointing up. Also, is ceiling steel better than wall? So this is referring back to earlier when I was talking about mounting access points on the ceiling. So yeah, you generally point them down. The mounting brackets go into the ceiling and the access points goes down because that's how the antennas are designed for. The antennas are designed so that the mounting bracket or the mounting holes go up, facing down on the area to be covered. And yes, ceiling is generally going to be better than wall unless there's a lot of obstructions up there, because again, the antenna patterns are going to be optimized for ceiling mount, not for wall mount. For positioning AP, it has to be above the drop ceiling. It doesn't have to be above the drop ceiling. The best place to mount it in most cases is going to be to mount it underneath the drop ceiling. But we have had a lot of our resellers out there who do these installations say, for one reason or another, their customer does not want them poking holes in the drop ceiling, or the customer does not want the access points to be visible. So as long as you've got a typical acoustic drop ceiling, not, you know, a tin drop ceiling or something like that, it's generally perfectly fine in those scenarios to just rest the access point on the drop ceiling, again, provided your local building codes allow that. Some places the building code requires that the device be plenum certified to be above the drop ceiling. Some places it's only within so many feet of the actual ceiling. Some places you are not allowed to have something resting on the drop ceiling. So it just depends on what your local building code is. But as long as it's allowed, it's generally going to be okay. Obviously, you want to set the access point sort of in the center of that acoustic tile, because your T-bars are normally made out of metal, and as we know, metal blocks and reflects signal. So you want to try to, you know, keep your access point away from other metal objects as much as possible. When are we going to see Wi-Fi 6E wall plate APs? Heck, I'd be happy if we just had a Wi-Fi 6 wall plate AP. I don't expect, at least from us, that you will see a Wi-Fi 6E wall plate AP anytime soon. We will have Wi-Fi 6 wall plate APs sometime next year, not anytime soon. The problem with 6E is just so few client devices actually support 6E. That's going to be one issue you run into. The other issue you run into is just the physical size. You're having to cram 3 radios, 3 sets of antennas into a small little box, and you may also have heat dissipation issues from that as well. That was definitely one of the problems we ran into with Wi-Fi 6 wall plate APs, is the first couple generations of Wi-Fi 6 chip just put out too much heat to be able to survive in those little wall plate enclosures. And we offer lifetime warranties on our products. So, you know, it may last a year or two, but it's not going to last a lifetime. So we will have Wi-Fi 6 next year. We're waiting on a new chip to come out, which is going to come out some point next year. And it just depends, you know, when that chip gets released to us from the manufacturer before we have the Wi-Fi 6. I would expect that we are going to skip 6E in wall plate and probably wait for Wi-Fi 7 for the next wall plate AP after 6. Question here is, does Wi-Fi 6E access points help with older devices? No. The only way it's going to help older devices is just by being able to move newer devices into a different RF spectrum, so they're not stepping on the toes. But you have to have those Wi-Fi 6E client devices first before you can take advantage of that. Will the WAC 6303D-S support Wi-Fi 6? No, the WAC 6303D-S is a 11AC Wave 2 product. So if you want a Wi-Fi 6 product, it's a similar configuration, you want to be taking a look at the WAX 630S. I think it's about $30 more than the WAC 6303s are, but that's going to be our smart antenna, our low-end smart antenna Wi-Fi 6 device. I'm asking where the benefit of 6E over 5 is. I think I got to that in slides already. Where is the setting for disconnected signal strength? In the Nebula interface, I think it's under the radio settings. Yeah, I think it's under the radio settings. I could be wrong, but you can reach out to your salesperson. They can help you out with that. I know Marcus has done some trainings on that. So just going back to the Cisco, if Cisco is using Rogue AP containment, I don't know of any technology solution that would override it. It's not something where we can battle them on. If they are intentionally creating interference on certain channels to try to contain neighboring devices, there's nothing that I'm aware of that they can get around that legally. Okay, I'll stick around for just a minute, but that is all of the questions that I've gotten today. So while I'm waiting to see if any more come in, let me draw your attention to our user forums, forum.zyxel.com, something we put together to allow you to talk to other Zyxel users and installers. However, unlike a lot of the other user forums that are out there, our R&D and our tech support do keep an eye on those forums. It is also generally the first place that any sort of security notifications get posted to and any sort of release notes get posted to. So it's a great way to keep on top of things. And if you are complaining about things or putting out feature requests, it is being monitored by our teams that do the product development so they can keep an eye on it. So if you can convince a bunch of people that your idea is a really good idea, it's much more likely to get implemented. So it doesn't look like we've got any more questions. I'm going to go ahead and end today's webinar. Thank you for joining, guys. Please join some of our future webinars as well. Thank you.